Okay. So, we have already started this constant flux linkage model, right, and we have come up to this because every lecture I start, this is already we have discussed, right. So, just and we ended up somewhere here, right. This is not required for you, right, and then we are starting from here, although we did it, but just we are starting from this last lecture whatever we ended from that page only. So, E d is actually minus R A I d plus omega L L I q minus omega L dash A q, or rather L A q dash in bracket minus I q plus psi 1 q upon L 1 q. All this terminology have been defined before, but I suggest one thing, whenever, because you are getting all the notes. So, just nomenclature other thing you put in front of you, because again and again if I try to repeat all the nomenclature or symbols meaning, then then it will be little bit monotonous, right. And therefore, E d is equal to minus R A I d plus omega in bracket L L plus L A q dash into I q minus omega L dash L A q dash in bracket psi 1 q upon L 1 q, and E d is equal to, therefore, we can make it minus R A I d plus x q dash I q plus E d dash. This is equation 214, right, and this is actually for my reference, this is not required for you, this is for my reference, right, where E d dash is equal to, we are defining this term minus omega L dash A q psi 1 q upon L 1 q, right. So, similarly the q x is stator voltage is given by, you go to those equations, right, whatever have been derived before, that E q will be minus R A I q minus x d dash I d plus E q dash, this is equation 216. So, this all this your this thing, no need to see this, this is for my reference, right, where E q dash is equal to omega L A d dash into psi f d upon L f d, this is equation 217, right. Therefore, with transient saliency neglected, that means when x d dash is equal to x q dash, right, the stator terminal voltage that you add equation 200 plus equation 206 you multiply by j. So, equation 214 plus j into equation 216, this mathematical manipulation we have to do, right. If you, I mean, that means we can make it E d plus j E q, that is equation 214 plus j into equation 216. So, it will be minus R A I d plus x q dash I q plus E d dash plus j in bracket minus R A I q minus x d dash I d plus E q dash. That means, this is my your E d and this is my E q, we are making is actually E d plus j E q, right. So, in that case, this equation can be written as E d plus j E q is equal to, say, capital E d dash plus j capital E q dash, right. This can be written as real, or what you call minus R A I d plus j I q plus x d dash in bracket I q minus j I d. We have assumed that salience is neglected. So, x d dash is equal to x q dash, right. Therefore, E d plus j E q, it can be written as capital E d dash plus j capital E q dash minus your R A, this is actually E d dash plus j equal to minus R A, okay, this is okay. So, minus R A I d plus j I q minus j x d dash I d plus j I q, we are assuming x d dash is equal to x q dash, right. Using phasor notation, we have your E t tilde is equal to E dash tilde minus R A plus j x d dash I t tilde, this is equation 218, right. So, this equation we are representing E d dash E d plus j E q is equal to E d dash plus j E q dash minus your R A I d plus j E q, right, and plus x d dash I q minus your I d dash, right, and E d dash and E q dash, E d dash here defined like this and E q dash here defined like this, right. So, and x d dash is equal to x q dash we have assumed. So, with this, using phasor notation, that E t tilde will be E dash tilde minus R A plus j x dash into I t dash tilde, this is equation 200, this is for my reference, no need to see this, right. Or E dash tilde is equal to, we can write E d dash capital E d dash plus j capital E q dash is equal to L A d dash minus in bracket psi 1 q upon L 1 q plus j psi f d upon L f d, because E d dash and E q dash we have defined, this is your capital E d dash, this is capital E d dash and this is capital E q dash, right. Just put those things in this equation, right. So, it will be like this. Now, the corresponding equivalent circuit is shown in this, right. This is your the E dash and this is my X D dash, this is R A and this is the current flowing to going to this load I T say, and this voltage is E T. So, that means this is the simplified transient model. That means this equation, that E T tilde is equal to E dash minus in bracket R A plus J X D dash I T tilde, and this is equation 218, right, and this is the corresponding your circuit diagram for that, right. So, this is the simplified transient model. Now, with rotor flux linkage, that is psi f d and psi 1 q constant, right, because it is a constant flux linkage thing. So, that means capital E d dash and capital E q dash are also constant. Therefore, the magnitude of E dash is constant, right. So, as the rotor speed changes, right, as the rotor speed changes, right, the d and q axis move with respect to any general reference coordinate system whose r means real, I means imaginary, that is real and imaginary axis rotate at synchronous speed as shown in figure 22. I will go to the figure 22. Hence, the component of your E r dash and E I dash your changes, right. So, that means when we go to that next thing, that this is actually your real axis, this is my real axis and this is my imaginary axis, right, and this is our d axis and this is q axis, right, and this is the omega r. Now, this is my E dash, this is my E dash, its component of capital E dash, its component on d axis is capital E d dash, is component on q axis this one capital E q dash, right, and it components on the real axis, that this is my real axis, it is E r dash, right, capital E r dash, and its component on imaginary axis it is capital E I dash, right, and this angle, that this angle is actually delta, right. So, this is your what you call, this is the real and imaginary and dq coordinate system, right. So, both are shown, real, imaginary as well as d and q, right. So, the magnitude of E dash can be determined by computing its pre-disturbance value, right. I mean, if you know the initial values, therefore, E dash tilde is equal to will be E t 0 tilde plus in bracket R A plus J x d dash into I t 0 tilde. This is equation 219, right. So, I mean, if you it can be calculated if you know the pre-disturbance value, right, because these are all your what you call the your transient condition. Now, its magnitude is then assumed to remain constant throughout the study period. For the sake of your simplicity, we will assume that it is constant throughout the study period. Since R A is very small, that is, it is neglected, right, it is usually to neglect it, right. Therefore, with the components E d dash and E q dash are each having a constant magnitude, this E d dash and this E q dash, right, each having a constant magnitude, and E dash will have a constant orientation with respect to d and q axis, as it is rotating, it is rotating, it is shown in that your anticlockwise direction, right. So, as the rotor speed changes, right, therefore, the angle of E dash with respect to synchronously rotating reference axis R I can be used as a measure of the rotor angle, that means this one, right, this delta. So, this model actually offers considerably computational simplicity. It allows the transient electric performance, right, of the machine to be represented by a simple voltage source of fixed magnitude behind an effective reactance. If we are assuming that R A is neglected, it is commonly referred to as the classical model, since it was used extensively in early your stability studies, because for the classroom purpose also we will try to use this model, right, and for the stability study, the simplified model. So, next is that reactive capability limits. Let me tell you one thing, if time permits, then at the end we will try to explain certain things, but at present I do not want to discuss this, then continuity will be lost. If time permits for this course, then at the end, that means at the end we will see the state estimations, and after that if time permits, then reactive to some extent we will try to talk about the exciter of the synchronous machine and the reactive capability limits of the machine. that is at the end if I find couple of hours time at the end, right, otherwise I have to skip this one. So, synchronous generators are related in terms of the maximum MVA output at a specified voltage and power factor, usually 0.85 or 0.9 lagging, right, which they can carry continuously without overheating. The active power output is limited by the prime mover capability of a, just a minute, the active power your what you call output is limited by the prime mover capability to a value within the MVA rating, right. The continuous reactive power output capability is limited by three considerations. One is armature current limit, right, another is that field current limit, another is end region heating limit, right. So, these three things, that armature current limit, field current limit and end region heating limit, if time permits, then at the end we will discuss that one, right, because it will consume some time, but here we will not discuss that, that continuity of this or what you call dynamics part will be lost. So, if time permits, I will do it at the end, right. So, next we will now we will come slowly and slowly we will enter to the dynamic stability, that is small signal stability of a single machine infinite bus system. So, for this course we will already study small signal stability of a single machine infinite bus system. Multi machine system, it is really as far as your what you call in the classroom is concerned, that multi machine stability studies is really too difficult one because of dynamic equations, all state variable equations, it will be very complicated one, right. But as far as classroom studies, we will only follow small signal stability of a single machine infinite bus system. Multi machine study, if somebody is doing research or master's project other thing, for that they can consider, but for the classroom study I will skip that one, right. So, small signal stability of a single machine infinite bus system, right. So, a general configuration is shown in figure 23A for the purpose of analysis, right. So, I will come to the figure, the may be reduced to the form of figure 23B by using Thevenin's equivalent of the transmission network external to the machine at the adjacent transmission line, and this is a simple general configuration is taken. Say it is a single generator, this is the transmission line having different branches, that your shunt branches are also there, right, that your all the it is represented in terms of impedances only in general, right, and here it is a large system is connected, a very large power system is connected. So, right. Now, if you try to make it a Thevenin equivalent one, so this generator is there, this generator will be there, and this is its terminal voltage E t, this is E t, this is E t, and this equivalent impedance, say it is Z d q is equal to R e plus J x c, right, and this bus we call infinite bus E b, that is the infinite bus we call, right. We will come to that what is infinite bus. So, this is actually equivalent system, this is figure 23, this is 23A and this is 23B, this is single machine connected to a large system through transmission line. So, this portion is actually your what you call, it is a transmission system and all are impedances shown, and their equivalent one is R e plus J x c, and this is a very large power system, right, and this is your terminal generator whose voltage is shown here E t, and this bus voltage infinite bus voltage is shown as your E b, right. So, we will go to the next slide, just hold on. Because of the relative size of the system, right, to which the machine is supplying power, because that is large system we are talking, that is your what you call. So, that is why because of the relative size of the system to which the machine is supplying power, dynamics associated with the machine will cause actually virtually your no change in the voltage and frequency, right, of Thevenin's voltage E b, right. So, that voltage, that infinite voltage, that Thevenin's voltage E b, because the large system is a huge system, right, and the generator which is connected, the dynamics associated with the machine, that is your sending end, that is the generator, right, will cause virtually no change in the voltage and frequency of the Thevenin's voltage E b. Such a voltage source of constant voltage and constant frequency is referred to as an infinite bus, right. This is the definition of infinite bus, right. I hope it is understandable. You have a generator and you have a that through the transmission line, the generator say it is connected with a very large power system, right, and in that case that if the dynamics are associated with the machine, that is the sending end, that is generator, right, actually it does not cause any change to the voltage and frequency of the last system. That is why the Thevenin voltage E B, actually that is called infinite bus voltage, and the frequency actually it will remain constant, both will remain constant, and that bus is actually referred to as infinite bus, right. So, now generator you are represented by the classical models. Therefore, we can write the same system that E dash tilde, this is x d dash I t, this is E t, this is x c, and this is E b angle 0. That means that your that is your that figure 23b, right, figure 23b, you have the generator, you have that your what you call, just hold on, I will go back to this figure once again, right, just hold on. This figure, right, this is my E t and this is my E b, right, and this is J d q R e plus this is infinite bus, and x d dash also you have to consider, right, for the generator, right, and this is my R e plus J x c, and if R e is neglected, suppose I mean sorry R a is neglected, only we will consider x d dash, right. So, this that means this is my E d dash tilde, this is E t, that is voltage behind transient reactance, right, x d dash, and this is x c and E b angle 0. R e we have not considered here, right, you have to this is x c and this is your E t and this is E b angle 0. I mean this voltage actually leading this voltage by an angle delta, right, and E t tilde, that is your E t tilde is equal to your E t 0 plus j x d dash into I t 0 tilde. This we have seen before, right, that pre-disturbance value, right. So, from which you can get that will remain constant throughout the study. So, E t tilde is equal to E t 0 tilde plus j x d dash I t 0 tilde. This I have told in the previous phasor diagram, right, and x t is equal to total x t is equal to x d dash plus your x c, right. Therefore, your what you call that with the generator represented with classical model, right, this is for my reference, this is not required for you. So, classical model and all resistances are neglected, the system representation, just hold on, system representation is shown in figure 24, where your E dash is the voltage behind x d dash, is magnitude is assumed to remain constant at the pre-disturbance value. Let delta be the angle by which it leads the infinite bus voltage E b, right. That means this one E dash tilde is leading this infinite bus voltage, that is by an angle delta, right. So, where E dash is equal to as the reference phasor, that means here your x t will be your total x t will be your x d dash your x t will be equal to x d dash plus x c, right. We have not considered R anywhere, assuming they are very small, right, for our your simplicity of the analysis, right. If this is E dash delta, this is E b 0. So, E dash actually leading E b by an angle delta, otherwise also you can put, suppose we can write this E dash, if you made this is angle 0 degree, then this one you can make E b angle minus delta, both are same, right. Here also your both are same, because if we make this is 0, this will be angle minus delta, because E b actually E dash leading E b or E b lags E dash by angle delta. So, E b lags E dash by angle delta, same way you can write. When you use the mathematical notation, we will use this one, meaning is same, right, meaning is same. So, therefore, with E dash as the reference phasor, that is I told you that I t tilde can be written as E dash 0 minus E b angle minus delta upon j x t. I mean here instead of this one, here I can take this is this thing, and this one I can take this is minus delta, right. So, if it is so, then this is my I t. So, I t will be, right, I t will be E dash angle 0 degree minus E b angle minus delta, right, divided by your x d dash plus then x t is equal to x d dash plus x c. So, we can write j, it is reactance. So, j divided by j x t, right. So, this way you can make that this is my IT your tilde, the phasor representation. Instead of writing, the other thing is also true that E angle delta minus E b 0 for our EG analysis, we have made the same thing, it is same actually, this the same thing, meaning is same, right. So, that is why this equation is written like this, that E dash angle 0 minus E b angle delta, this is actually minus E b your what you call cos delta minus j sin delta upon j x t, right. So, now next from that the complex power behind x d dash is given by S dash is equal to, you know, this is your P plus j q is equal to E dash tilde then I t conjugate, right. So, this one if you just try to do it, I am just making it for you, right. So, this is nothing, this is for my reference, this is your E dash minus E b cos delta minus j your sin delta, right. So, numerator and denominator first you multiply by your what you call this one I can write like this, E dash minus your I am writing over it E b cos delta, right, and then plus your minus plus then j then E b then your sin delta divided by j x t, right. This is your full thing, right, divided by j x t. Now, in this case, so this is my your what you call that your I t tilde is equal to, right. Now, question is that numerator and denominator you multiply by j, numerator and denominator, and simplify. If you multiply numerator and denominator by j, so it will be something like this, say minus, because j denominator j square will be minus 1. So, it is minus and multiply this one by j. So, and this one if you multiply by j, right. So, it will be j square. So, it will be minus E b, it is sin, right, E b sin delta and then your plus j your E dash, just hold on, E dash minus your E b cos delta, right. So, this is your, you just multiply numerator and denominator by j, right. So, this will be j square. So, that is why it is minus and here it will be j square. So, minus E b sin delta and here it is j means j into E dash minus E b cos delta, this one, right. Now, if you just multiply this one by minus, then this should not be there, this should be plus E b dash sin delta, right, and divided by of course your x t, right, divided by your x t, right, and this will be your, instead of j it will be minus, right. And if you take its conjugate one, because p plus j q is equal to E dash tilde I t conjugate, if you take its conjugate one, then it will be basically E b sin delta minus j your into your E dash minus E b cos delta upon x t, right. So, if you do so, then just hold on, right, if you do so, then what will happen that your complex power that p plus j q is equal to E dash tilde I t conjugate. Now, I t conjugate will be and your what you call, it will be basically E dash E b sin delta, because it will be multiplied by this one E dash E b sin delta, because we have taken this one that your E dash tilde is equal to your E dash angle 0 degree, right. So, because we have taken that E b angle minus delta. So, with that here you put an I t conjugate you put and you simplify whatever I showed, you will find that E dash E b sin delta upon x t plus j E dash into E dash minus E b cos delta upon x t, this is equation 221, right. So, that means my p is equal to E dash E b sin delta upon x t, and q will be equal to your E dash into E dash minus E b cos delta upon x t, but our interest is now only with that real power. E dash, the way you have studied for power transfer, no, V 1 V 2 upon x sin delta. So, it is the same thing, right. So, with this stator resistance neglected, the air gap power P is equal to the terminal power. This we have seen earlier, that P is equal to your what you call that air gap power equal to the terminal power. So, in per unit the air gap torque is also equal to the air gap power, that also we have seen before, right. Therefore, that T is equal to P, because it is per unit, right, that will be E dash E b upon x t sin delta. This is actually equation 222. This is not required for my reference, right. So, this is the same thing whatever you have studied in your third year undergraduate power system course, that is your V1 sending and receiving V1 V2 and resistance is neglected and the reactance is X. So, it is V1 V2 upon X sin delta, same thing here also, expression is same, and in per unit torque is equal to power. So, T is equal to P E dash A B upon X T sin delta, right. So, if you linearizing about an initial operating condition represented by delta is equal to delta 0, that means this your what you call this equation, suppose this is my T equation, because in per unit is E dash E b upon x t sin delta. Now, if you take delta T, you can write that delta T e upon delta delta into your delta delta, right. That means that this delta delta I can put here, just hold on, I can put here. It is at the suppose an initial operating point is given delta is equal to delta 0, this one actually delta is equal to delta 0, right. Therefore, if you take the your what you call that T is equal to E dash E b upon x t your sin delta. So, if you take delta T upon delta delta, that means your T is equal to your E dash E b upon x t, then just hold on, x t into your sin delta, right, sin delta. Now, if you take your delta T upon delta delta, that is E dash your E b upon x t your cos delta, and at delta is equal to delta 0, this will be delta 0, right. So, that is why this is your delta t is equal to delta t delta delta into delta delta. So, E dash E b upon x t cos delta 0 into delta delta, this is equation 223, right. The equation of motion we have seen earlier in per unit, that is your, this is not required for you. So, this we have seen earlier, P delta omega r is equal to 1 upon 2 h in bracket T m minus T minus k d into delta omega r, this is equation 224. This one also we have seen P delta is equal to omega 0 into delta omega r, this is equation 225, this is for my reference, right. So, let me clear it. And where delta omega is the per unit speed deviation and delta is the rotor angle in electrical radians, right. This we have seen earlier. So, omega 0 is the base rotor electrical speed in radians per second, right. And we know P is equal to, that is your what you call d dt, we have represented by this, right. So, differential operator, but later we will replace by Laplace domain. So, we will put in, we replace P by S, right, and T in second. So, equation 224 can be written as that P delta omega r is equal to 1 upon 2 h is equal to your into delta T m minus delta T minus k d into delta omega r. I mean, this equation P delta omega r, again we can write 1 by 2 h T m minus T minus k d delta omega r is there, right. But if you take again, this can be written as P delta omega r is equal to 1 by 2 h delta T m minus delta T minus k d delta omega r. The how things are, how this from everything is same, but just we are making delta T m minus delta T, the small perturbation, how things are coming, how these two things are coming, we will come back in the next lecture. Thank you.